3 sigma over 4 at some point, right? At some point. Now if I choose lambda and epsilon small enough, very small, this is going to be very small. So for 0 less than epsilon, lambda, very small, I'm going to have that supremum of phi x, y, t s going to be greater than equal to the supremum of phi x, t, t. Because I have more room to vary here compared to fixing it. So it's going to be greater than equal to sigma over 2. In other words, the supremum of this one is going to be greater than sigma over 2. And now look, because of the penalization, t and s cannot go to infinity. This one is going to go to minus infinity. X and y cannot go to infinity. This one is going to go to minus infinity. So that means the supremum is achieved at some point, which is the maximum. So there exists x0, y0, t0, x0 such that phi x0, y0, t0, s0. I haven't done anything. This is just a preparation step. You're going to see the plan ideas later. It's the maximum of 3. And it's going to be greater than equal to sigma over 2. So the axis is the maximum point because I penalize it. I don't allow it to go to infinity. Okay. Now, because I can vary x, y, t as any way I like, so let's plug in some specific value and see what's going on. So the first thing we have is that we have phi x0, y0, t0, s0 is greater than equal to phi 0, 0, 0, 0. F1. Nothing else. When everything is 0, this goes to y, this goes to y, goes to y, goes to y. Everything 0. So what you have is just this thing. So you're going to have u of x0, t0 minus u2 of y0, s0 minus x0 minus y0 squared plus t0 minus s0 squared over epsilon squared minus lambda t0 plus s0 minus epsilon x0 squared plus y0 squared greater than equal to 0. Everything is 0. I think so. Let me know if I did something stupid. Okay, this is still a preparation step. I'm trying to derive some bounds for x0, y0, t0, s0. It's not yet the main step. Okay, I'm going to do it quick now. So from here, what you're going to get is that we assume that this guy and this guy are bounded, right? So you're going to have this whole thing is bounded. So okay, this is bounded. We assume from the assumption this is bounded. So each of this is less than equal to c, less than equal to c. So what we're going to have is that x0 minus y0 squared plus p0 minus s0 squared less than equal to c as 1 squared. And we're going to also have, just take that guy, x0 squared plus y0 squared less than equal to c over epsilon. That's the epsilon, this is less than equal to c. Okay, so this we're going to easily get x0 minus y0. Okay, don't worry, this is just a kind of boring step. So you see, this is what I mean by penalization. When I let epsilon goes to 0, those guys have to be closer, 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 closer. Right? They have to be the same. That's what it means by saying penalization. Penalization means I want to penalize so that something that I notice together. Okay, the second thing I'm going to test, I'm going to omit this step. That I have phi x0, y0, p0, s0 is greater than equal to phi. Now I'm going to test x0, f0, t0, t0. Okay, those are just, because you have this maxima, so why don't you plug in anything to test? So if you were to test this, you're going to end up with something like this. You're going to end up with x0 minus y0 plus p0 minus s0 is actually, well, I have to write I have to do this square over epsilon squared is less than equals to u tilde of x0 t0 minus u tilde of y0 s0 plus lambda of t0 minus s0 plus epsilon x0 minus y0 x0 plus y0. By plugging in, you have something like this. Now, what I mean is that this one converges to 0 and epsilon goes to 0. This one converges to 0 and epsilon goes to 0 because they're close. U tilde is continuous. x0 and t0 are close to y0 and s0, so this is sort of also small and converges to 0 and epsilon goes to 0. So the whole thing I can call it omega epsilon. So this is modulus of continuity. And that means omega epsilon converges to 0 as epsilon goes to 0. Okay, that means I have a method estimate. I have x0 minus y0 plus p0 minus s0 is less than or equal to epsilon, omega epsilon. So up here I have that it's bounded by c epsilon. Down here I have this kind of method, technical. Okay, so now let me do the t step, and I think that's okay. Now let me do the key step, and you're going to see why it is so clever. I know that you have time, but bear with me for 3 more minutes. So the third step, this is why I call doubling variable. Oh, here. Now I'm going to freeze t. I'm going to vary y and s, for example. Or the other way. I'm going to freeze y and s. y0, t, s0. Okay. I'm freezing y0, s0. I'm varying x and t. This one has a max at x0, t0, isn't it? Right? I'm freezing two variables. I'm running x and t over. Surely this one still has a max at x0, t. Right? So let's see what's going on if I'm freezing y0 and s0. Look like here. What do I have? So that means I have u xt minus u tilde y0 s0 minus x minus y0 square plus t minus s0 square over epsilon square minus lambda t plus s0 minus epsilon x square plus y0 square as in max. Max, a strict max doesn't matter, by the way. F x0, t0, and t that's. Okay. You see, this is so clever because when I free at y0 and s0, this is just a constant. Now I have u minus some smooth function here as a maximum at this point. Okay? Alright? Everything is polynomials. So now I can quote the definition of subsolution, right? This one has max. So that means the test function blah 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 has to be less than 0. Blah blah blah. Right? So what is the time derivative to this one and this one? So I'm going to have t0, so by subsolution, the definition 1 of subsolution, I differentiate that with respect to t to have the time derivative, t0 minus s0 over 2 epsilon squared plus lambda. This is a time derivative plus h at x0. So where's the space derivative? Again, this is constant, this is constant, this is constant, it doesn't matter. Space derivative coming from this and this, so I have x minus 0 minus y0 over 2 epsilon squared plus epsilon 2 epsilon x0. Let's make it. So this is. I do the test function, but because I do that variable, when I freeze y0 x0, I don't see the not differentiability of this thing. I only see it through the test function, through the analyzation. So I have something to do. Don't worry. Now, 4. Now, I'm going to freeze x and t, vary y and s and y s maps to feed x0, y, t0, s and maps, and y0, s0. Right, right now, get